Hi everyone, this is Emily Smith and today I'm going to be giving a presentation on the paper called SysPal, System Guided Pattern Locks for Android. First we're going to go over some background information. So the Android lock screen is a lock screen that features a 3x3 grid of dots, which you can see on the right hand side of the screen. That users can interact with to set an Android pattern lock. Pattern lock is created basically when a user swipes their finger across each of the dots in a specific order, creating a pattern that acts as a password or a passcode to unlock the phone. There are 389,112 password combinations that are possible given the 3x3 grid, which does make the grid more secure than a typical 4-digit PIN code. However, the password grid is still relatively crackable, with a password space that is much smaller than the possible 389,112 password options. This is because users tend to have biases that result in them choosing one corner of the lock screen as a starting point or an ending point, as well as choosing certain numbers of points to use in their passcode. Now, how do we reduce password crackability? Research has investigated the use of a larger grid to reduce password crackability, but even with a 4x4 grid, 20% of passwords are easily cracked. This is because, as I said before, users are biased in their choice of passwords, choosing typical starting positions or ending positions that make their passwords easier to guess. So, what can we do to encourage users to create more secure passcodes? SysPal is a system that seeks to answer this question and provide a solution. SysPal is a system-guided pattern lock scheme developed by the Department of Computer Science and Engineering at Sungkyunkwan University. It works by setting randomly selected points that users are required to use when selecting a lock screen pattern. This is to say that essentially there are a number of points that are highlighted on that 3x3 grid that the users must incorporate it, and that it is mandated that they do so. They do not need to start at any of the specific points, and they do not need to end at any of the points, but all the points that are listed must be incorporated into their passcode. SysPal has a few goals. First, they want to make passwords that are easy for users to remember. They don't want to result in passwords that are more complex and hard for users to remember, because if users are unable to remember passcodes, that increases the difficulty and memory load on users, and essentially will make the password model less usable. SysPal also wants to maintain the unlock and authentication time. So compared to the original or typical model of Android system passcodes, which is to give you no guidance, the SysPal model that is being introduced wants to have the same unlock and authentication time and have the users take the same amount of time in using SysPal as they would in the original Android system. SysPal should also be easy to use and intuitive, and it should also be a self-contained system that is not going to require any changes to the hardware or software on the operating system. So essentially, SysPal should be very easily integrated into the existing OS so that there's no additional steps that users need to take or additional steps that developers need to take to implement this additional security measure. So in comparing SysPal to previous solutions, SysPal's system is unique because it requires users to use these randomized points on the pattern of the lock screen. But it also lets users choose where in the pattern those points will go. So it doesn't list a certain number of points and then require users to start or end on any of those points, but simply requires that users incorporate the listed points into their passcode in some way. So a little bit of background terminology. This is just going over what we've talked about a little already. The Android lock screen, which features the 3x3 grid, which you can see over here on the left-hand side of the screen. During the presentation and as well in the paper, we will also use corresponding numbers to refer to each of these positions, which are not demarcated in any special way on the lock screen. So we'll simply use the corresponding numbers here on the right screen to refer to the same points on the left. Also on the left-hand side here, you can see that there are certain lines that are connecting these various points. These are going to be called segments during this presentation. And additionally, we will note that points for these passcodes can only be used once. So once one point is included in the passcode, the user cannot re-reference that point further along in the passcode. For instance, saying 1213 would not be a valid passcode, but you could say 1233. So a little bit more on background and threat modeling for Android patterns. So there are a variety of known attacks that can be used to unlock Android phones and guess or otherwise sidestep these Android patterns that are used to unlock phones. These include smudge attacks, sensor-based side channel attacks, shoulder surfing attacks, and guessing attacks. This paper specifically focuses on thwarting pattern dictionary-based attacks, in which the most common passwords are found by an attacker, and those same passwords are tried on a user's device to see if it can be unlocked. A little bit on cracking the password. Android employs techniques to prevent password guessing. So essentially, when a user inputs the incorrect password 5 times in a row, the phone will become locked for 30 seconds. If they input 20 failed attempts, then the phone is locked until the user can log into their Google account. Because of these mechanisms that Android already employs, this paper essentially says that there are 20 attempts that an attacker can make, and makes that assumption in all viewpoints of looking at security and other implementation. So a little bit of the overview of the methodology for this paper. So the main research question that they're attempting to address is, can we design security policies for Android screen lock patterns to improve their security without significantly compromising their usability? So there are 3 hypotheses that are posited at the beginning of the paper. The first is SysPal pattern security strengthens as the number of required points increases. So essentially, as more points are mandated that a user must use, the security and the difficulty in a user attacking the phone and guessing the password will increase. The second hypothesis is that SysPal pattern memorability decreases as the number of required points increases. So essentially, as more points are required, it makes it harder for users to remember the password that is created. The third hypothesis is, if there is no difference in memorability between a SysPal policy and the standard Android patterns, the SysPal policy has better security. And that's something that we will get into a little bit further in this paper. The following studies that are going to be discussed in this presentation were studies that were designed to test these hypotheses. So essentially, there are 5 main policies that are investigated throughout the paper. The first is the original policy, which is the standard Android policy that does not require any certain number of points to be used. The 1, 2, and 3 point policies each require 1, 2, or 3 points that a user is mandated and required to use when they are creating their password. The third option is a random option, which is considered to be the security ideal. It randomly decides which points, as well as how many points, are required for the user to use when unlocking their phone. This is essentially a snapshot from the paper that is just reiterating in more detail what we just went over of the different types of policies, if you need to reference that. So this paper consists of 2 studies. The first is an online study, and the second is an in-person study. So for an overview of the online study, it was conducted using Amazon Mechanical Turk, which is a website that allows users to take surveys in exchange for small amounts of money. Think, 10 cents to $5 is the standard. For the study, they were able to recruit 1,717 participants by offering them between $1.50 and $2 in compensation. There were 3 time intervals that were measured, which were 2 minutes, 15 minutes, and 24 hours. This study was designed to test the memorability of lock screen passwords for each of the different policies across participants. In order to conduct this study, the research team developed an Android app that mimicked the password setup and login process. of a Android lock screen with the SysPal mandated points included. So a typical participant actions for the study. So each participant would go through and do these actions in the following order. They would generate a password where each user was assigned one of the SysPal policies, and they would have to follow that SysPal policy in developing their password. They would then draw the pattern twice to help them remember it. They would then create they would go through a puzzle of some sort for 2 minutes. That is essentially to stretch out the time, distract them, and make them think less about the password directly. Afterwards, they would complete some demographics information. And then they would be asked to draw the initial pattern with 5 possible attempts, which we remember is the number of attempts allowed before the 30-second lockout on the phone. Afterwards, they would complete a brief survey. After participants were able to complete these steps, steps 5 and 6 of drawing the initial pattern and creating a survey were repeated after 15 minutes and after 24 hours. In this study, 15 minutes was selected based on the assumption that users interact with their phone 57 times a day, where there are 14 waking hours in a day, resulting in about 1 interaction every 15 minutes. So this is the typical period that users would go between interacting with their phone in real life. 24 hours was used to say that essentially users must interact with their phone once a day, and therefore at least once a day, and therefore the 24-hour period was selected as kind of the longest time period a user would go. So based on this initial study, the following data was collected. They collected the policy for each user, the pattern the user used, the number of initialization attempts, so the number of times the user reset the grid during setup, which they could choose to do before selecting a passcode. So for instance, if they were given 3 points for the 3-point system that they were not interested in using, they could reset the grid to get a different 3 points. Data was also collected for the unlock attempts, the number of unlock attempts that happened, the time taken to set up the pattern initially, as well as the time to authenticate, pattern recall results, and essentially whether the user was able to remember their pattern, as well as the survey answers. So this is going over the demographics of users. 71% of the participants were white. A majority were between the ages of 18 and 39. Just over 50% were male. And a majority of users graduated from at least high school, with 54% graduating from college as well. So first we have the recall success rate. The recall success rate is essentially whether the user was able to remember their password, and was measured in the number of remaining participants divided by the total number of initial participants. So based on each time, you can see that for participants at 5 minutes that were assigned the random method, 17% of them were not able to remember their passcode, whereas only 0.5 to 2% of participants were unable to remember their password and other policies. This is a very large and significant difference between random and the other policies. For 15 minutes, 95% or more of participants were able to remember passcodes for any of the SysPal 1, 2, or 3-point systems over the original policy, whereas about 80% of participants for the random policy were able to remember their passcodes. After 24 hours, you can see that the recall success rate continues to dip across the board. 70 to 74% of users of SysPal and original policies were able to remember their passcodes, whereas only 51% of users that had the random policy were able to remember their passcode. For all of these time points, they saw there was no statistically significant difference between the original and SysPal policies in regards to recall success. Here's a visual representation of what we were looking at on the previous slide. You can see that the recall or the authentication time increased for users in the random policy, so it took them longer to be able to unlock their device than it did in other policies, which were relatively comparable. And this is a trend that we can see over the 2-minute time period, 15-minute time period, and the 24-hour time period. For authentication time, we also see that all policies were statistically significantly better than the random policy, where there was also no difference statistically significant between the original and SysPal policies in the 2-minute interval. For the 15-minute interval, there was no significant difference between test 1 and 2, except for the random, which significantly decreased. There was a significant increase in authentication time for all policies after 24 hours, with a significant difference between random and other policies. So again, the other policies are not significantly different from each other, but the random policy does take longer time to authenticate. So for pattern setup time, we're essentially looking at how long it takes the user to initially set up a pattern. We can see here that random has a longer setup time than other policies, and this was also found to be statistically significant, where other policies were comparable. For usability results, pattern initialization. Users could reset the grid or initialize it as many times as they wanted to. Again, we see that original and SysPal policies had a similar number of pattern initializations, where the random pattern had significantly more. And for recall difficulty, this is a nice graph that shows how difficult it was to recall the passcode for each of the different systems. So we can see that for 3-point, 1-point, 2-point, and original, a majority of the patterns were easy to recall. There were not very many people that had difficulty in recalling it, but for random, there were a large percentage of people, almost 25, that found it difficult or very difficult to recall their password. In regards to security results, other studies have showed that people are biased when selecting patterns, choosing patterns with common start and end points. This study specifically looked at the common start and end points for each policy. So here we can look at, this is showing the usage ratio for each of the 9 points across different policies. So we can see that in all of the first 4 policies, original 1, 2, and 3-point, there is a bias for using this center point, or the 5 on the grid. Whereas in random, that bias goes away a little bit, and it's a little more spread out across the board. Again, this is looking at the ratio of each point being used as the start point. Across the board, we can see that the 1 position is favored in all of the pattern modeling. And the endpoint, again, the 9 position is favored across all of the different models. Overall, the 5-point system was used more frequently in SysPal policies than in the original policy. And there were no statistically significant differences for start and end points in SysPal policies compared to the random policy. They all tended to use the same first position for start and 9th position for end. In regard to segments and security, all SysPal policies had similarly used segments. For example, the segment between 2 and 3 and the segment between 1 and 2 are most commonly used in all policies. There were some diagonal segments that weren't used at all, such as between 9 and 4 and 1 and 8. A metric called Shannon entropy was calculated to determine the usage frequency of the segments, where the 1, 2, and 3-point all had entropy around 5.1 to 5.2. And found that the SysPal patterns were distributed more evenly than the original patterns. Random had the highest entropy of 5.8. Higher entropy means that essentially the passcodes are more random, and therefore they're more difficult to crack. So this is a heat map that's showing the pattern visualization of these segments that we discussed in the previous slide. So a little surprisingly, the random model did not have a perfectly uniform distribution of points. In the paper, the researchers hypothesized that this could be because users could refresh unlimited times at the beginning until they found a random pattern that they liked and then choose it, which allowed user bias to leak into the model. in regards to security results, pattern characteristics, and the mandated point usage. We did see that there was a somewhat bias in the 1 point and 2 point options where users tended to use one of the points as the starting position. On the 2 point method, 39% of users used one of the points as the first position and 19% used it as the second position. In the 3 point model, surprisingly, it's a little more evenly distributed, where points were primarily used in the second and third positions. In security results and how to guess entropy, the researchers had partial guessing entropy estimated to essentially account for attackers that want to steal a portion of the password set. And this algorithm here is showing how the partial guessing entropy is calculated. They also used a Markov model to estimate the likelihood of the occurrence of each pattern with a different model built for each policy. So they took the top 20 most common passwords that are calculated and then looked at the graph here that kind of shows the probability of each of these passwords. The original patterns tend to be skewed toward a smaller number of passcodes that make them more easily guessable. You can see here in regards to entropy, random had the highest guessing entropy, whereas SysPal policies all were significantly less guessable than the original policy, which is down here. So as you have higher entropy, the number of guesses required to guess the password increases. So you can see that all of the 1, 2, 3 point and the random had significantly higher entropy and higher required guesses from an attacker than the base policy. The 1 point policy had the lowest entropy, followed by the 2 and 3 point policies. SysPal passcodes show increased entropy compared to the original, meaning that they're more robust against attacks. The results of this study showed that SysPal passcodes are more resistant than the typical 4-digit PIN codes and are significantly lower than real-world 6-digit PINs. In regards to pattern cracking, researchers applied a 10-fold cross-validation onto each set of patterns using the top 20 most common passcodes. There were no random passcodes that were cracked. This was found to be the most robust method. 33% of original passcodes were cracked using this method, whereas 10% of 1 point, 9% of 2 point, and 14% of 3 point passcodes were cracked. SysPal was statistically significantly more robust than the original model, but there was no significant difference between the SysPal models of 1, 2, and 3 point. The second study was a lab study, which was a smaller study with only 46 total participants recruited at a university campus. This study was designed to show the typical usage, where each participant downloaded a SysPal app and had to use it for 24 hours to mimic the real life usage. This focused on the original 1 and 2 point models only. The results of the study, there was only one person who failed to unlock their phone. There was high survivability in all methods, meaning that the number of attempts that were made were generally successful between 92.3 and 93.8% of the time across policies. 99.9% of unlocks were successful in all policies. The original method did outperform 1 and 2 point policies in the time it took to unlock phones, with the original taking 2.16 seconds and the 1 and 2 point policies taking about 2.5 seconds. Of original setup time for the passcodes, the original time was the shortest, taking only 12 seconds. 1 point took 27 seconds, and 2 point took 32 seconds. They found that the 1 and 2 point setup time was not significantly different from each other, and the mean number of initializations was not significantly different between the different policies. Discussing security improvements, SysPal pattern security strengthens as the required number of points increases was the original hypothesis. This study found that the number of points did not increase system security. However, SysPal policies were more secure when compared to the original policy. Unexpectedly, 1 and 2 point models had fewer cracked passwords than 3 point. Users tend to connect the mandated points directly instead of simply including them in the password, which may have introduced pattern selection bias in the 3-point model. The result of this is that the first hypothesis is rejected. For recall success and memorability, the second hypothesis was that SysPal pattern memorability decreases as the number of required points increases. However, increased mandated points don't seem to decrease the memorability of patterns. SysPal patterns may be just as memorable as the original patterns. Therefore, we cannot accept the second hypothesis. The third hypothesis: if there is no difference in memorability between a SysPal policy and the standard Android patterns, the SysPal policy has better security. We did see that SysPal and original policies had similar recall ability, and SysPal policies were significantly more secure than the original policy in regards to partial guessing entropy and percent cracked patterns. The result is that we can accept the third hypothesis. A little bit about related work. There are graphical passwords such as Passcode that can be used on Android and similar devices. Additionally, password strength meters have shown to be successful in increasing user password strength. SysPal is similar to graphical passwords and similar persuasive techniques that have been developed where users are suggested to use points, but it does require users to use these points, which makes it a bit more secure. In conclusion, the suggestion is to integrate the 1 or 2 point SysPal system into Android OS to increase security without compromising memorability. Use similar graphical password schemes to increase security in other types of passcode systems. For future work, they look to explore pattern features such as length and design additional models for other types of passcode systems. And that is the end of my presentation. Here is the reference to the original paper if you would like to read it. Thank you.